Today we are talking about parent functions, and we talked about them a little bit last week when we did the graphing the absolute values, and I talked about how when we were graphing that absolute value of x, it was considered a parent function because it was like the simplest version of an absolute value, right? It is just the absolute value of x. Nothing was happening to that absolute value. And so we're going to kind of talk about that with all of the different types of functions that we have. Um, so a linear function is when we have a value that is f of x equals x. And what that means is that your y value and your x value are the same. So if I put in 0 for x, my y value will be 0. If I put in 1 for x, right? So if I put in 0 for x, my y value is 0. If I put in 1 for x, my y is 1. And it winds up just being the graph of a straight line. And that works in the negative too. -1 would be -1. -2 would be -2, right? Now let's see if I can connect the dots. That's my worst part. And this winds up just being this straight line on the diagonals. Whoops. In both directions. Now, I'm going to erase that little bit because look at the notes later and be like, what the hell is that? So that's kind of how, and that looks like a straight line, right? Well, it should look like a straight line. If I had a ruler, it would be a straight line. But you get the idea, like it's consistent. It's following, it's got a very specific slope, right? Whatever my x is, that's also what my y is. Doesn't matter where that line starts. Up here, the things we're talking about, D is for domain, right? All of your possible x values, we've talked about that before. And R is for range, all of your possible y values. And if you look at this, the domain is referring to what's going on left to right. And if you look at what's going on to the left side, we can keep going on the left forever, right? And we would call that, the domain is -infinity to infinity. Or we could say it's the set of all real numbers. That is a sufficient response. So the domain is, look at your arrows. What's happening going from left to right? In this case, they don't end in either direction, so it's all real numbers. Our range, it's what is happening up and down, right? And again, on this one, this arrow goes up forever. This arrow goes down forever. So our set, our range would also be all real numbers, or we could say -infinity to infinity. Does that make some sense? I don't see anybody's face, so I'm just going to assume that it makes sense because y'all are just blank, even though you shouldn't be, but I'm so tired of fighting. X-intercept. Our x-intercept is where the line crosses the x-axis. And in this case, where that is at point 0, 0, right? The only place that it crosses the x-axis is at 0, 0. Our y-intercept is where it crosses that up and down axis. And in this case, again, it's also crossing right here at y equals 0. So again, our y-intercept would be 0, 0. The maximum number of roots. Now, you don't need to know this for right now, but we are about to get into it. And roots really are just how many times it can cross the x-axis. Because we're about to start getting into things that kind of graph like this or like this. You want to know how many times can it graph the x-axis. This one, the only time it'll cross the x-axis on a linear function is once. You can't have more than 1 0 in a linear equation. And that's what we're talking about with roots and zeros. They're just x-intercepts. How many x-intercepts do you have? And you can look at that and go, oh, it only crosses that line once. Now, end behavior is saying what's happening to the arrow, right, as x approaches. The first one that we're going to say is as x approaches infinity, right? And then the other one will always be as x approaches negative infinity. So we're saying what is happening to y as x gets bigger and bigger. X goes in, as our x's move this way, right? What is happening to our y? And for us, it is going towards infinity up, right? And that's what this means. This means as x approaches infinity, as x gets bigger and bigger, what's happening to y? And for us, y is getting bigger and bigger. How far? All the way to infinity. Now, when you do your homework on this, you're not going to have to remember all of this information, but it's good for you to have as we move on. For the homework assignment you have in Delta Math, you just have to be able to look at a graph and tell me what the parent function is, which is why I said it helps to have this information in front of you. But like you don't have to remember all of this stuff that's happening, but it will help you as we move on throughout this unit. Now we're saying what is happening to x as x is getting smaller and smaller as it's heading in this negative direction, right, towards negative infinity. What's happening to y? And y is going down for a length of infinity. It is approaching negative infinity. Now this continuous, discontinuous, this is really easy. If your graph is broken in any spot, it's going to be discontinuous. But in this case, our graph doesn't break. It goes on forever and ever. And so this would be a continuous function. And that's literally all there is to it. We did some discontinuous with the piecewise when we were first doing those piecewise functions, but linear will always be continuous. It's always going to be a straight line. So absolute value, this is another one you guys have seen before. Absolute value was that f of x equals the absolute value of x. And if you remember, this one went like this, right? If I put in 1, I get 1 out. If I put in 2, I get 2 out. If I put in negative 2, I get 2 out. And we wound up with this graph of v, right? And anytime you see that v, you're pretty much going to know that it's an absolute value function. It's really kind of the only thing that makes that shape on the graph, at least at this level. So if we talk about our domain, right? Domain is what can x be? And in this case, x can be anything negative and it can be anything positive. And we know that just by looking at the arrows on that graph, right? It's going to the left forever and it's going to the right forever. That's what those arrows mean. And so in this case, our domain, again, can be all real numbers. That's just the set of all real numbers. Or we could just say negative infinity to infinity. But our range is different this time because both sides go up forever, right? But not a single point on this graph goes below that x-axis, right? So our range really goes from 0. It can equal 0, so we'd have a bracket, all the way over to infinity, which is always a parentheses, right? It has a stop and starting point. We could also say that y is greater than or equal to 0. Any way you want to say that, it means though that in this circumstance, y can't be less than 0. Now, in other absolute value problems, it can be, right? Because we can move x and y up and down. We learned that the last time. But in the parent function itself, the absolute value of x isn't going to go below that 0. Our x and y intercepts, the only place it's crossing that line at x is at 0, 0. And that would be true for the y-intercept too. The only place it crosses the y-axis is at 0, 0. Now, the maximum number of roots that this one can have, notice it goes up in that V fashion, right? So if this graph were moved down, right, it has the potential to cross that x-axis twice, which means it can have a maximum of 2 roots, right? Because it does have the potential to cross that x-axis more than one time. And again, now we're talking about end behavior. We're saying what is happening as x approaches infinity. So as x gets bigger and bigger, what is happening to y? Is it getting bigger or is it getting smaller? I want some answers in the chat box. Bigger or smaller? Are the arrows going up or are the arrows going down? As x is going towards infinity, so as x is moving in this direction, right? My x's are getting bigger. What's happening to y? Yeah, it's going up, so it would be getting bigger, right? So y is also going to infinity. And if we look at the other side as x is getting smaller, so now x is moving in this direction. We're saying what is happening as x approaches negative infinity? As x is moving to the left, what is happening to our y? And again, it's going up forever. So it would be getting bigger. Oops. And therefore it's approaching, in this case, it's approaching positive infinity, right? Because it's going up, it's not going down. Is it a continuous function? Yes, it is, right? There's no break in that. There's a turn in it, right? Where at that V, there's that vertex where it turns. But there's really no break in that graph, right? It's still continuous. It goes forever and ever. The quadratic function is f of x equals x squared. And it graphs, think about this. If I plug in 0 here for x, I'm going to get 0 out. If I plug in 1 for x, I'm going to get 1 out. If I plug in 2 for x, well, 2 squared is 4, right? And the same with negative. If I plugged in negative 1 there and I squared it, I would get positive 1. If I plugged in negative 2, I would get positive 4. Similar to an absolute value equation, a quadratic equation is also symmetric, right? What's happening on one side is also happening on the other. Except for this should be a smooth curve that connects it. Mine looks a little V-like, but it should be a curve. But if we look at the domain and range, are what's happening to X, what can X be, and what can Y be? If I look at this, the arrows still go in both directions, right? They're coming out narrower now, but they still go forever to the left and forever to the right. So again, this one is all real numbers. But notice nothing happens under this X bar right now. So in terms of the parent function, this parent function starts at y equals 0 and can go up forever, but doesn't go down. So we would have y is greater than or equal to 0. Or we could write it as bracket 0 to infinity. Both of those things are an accurate way of expressing it. Our x-intercept, it's only crossing the x-axis in one spot. That would be 0, 0. Same for the y-intercept, right? It's only crossing y at one spot. Now, would every function do that of this? No, because they can be moved around. But in terms of the intercepts of the parent function, those are the only points where it crosses. Maximum number of roots and zeros mean how many could we have? Like what is the highest potential? And because this can cross in two different spots, again, we have two things going in the same direction, right? Both up on both sides. It means we could have two roots. And as x approaches infinity, right, as x gets bigger, y also goes up to infinity. And as x gets smaller, as x goes off to the left, right, in that direction, y still gets bigger all the way to infinity. And there are no breaks in this function, so it is continuous. Cubic square root, let me see what we've got here, cubic function is something to the third power. So that would be f of x equals x cubed, right? And when we're dealing with an x cubed, now think about this. If I plug in 0 for x cubed, I'd still get 0 out because 0 times 0 times 0, still 0. If I plug in 1, right, I would still get 1 out because 1 times 1 times 1 times 1, it doesn't matter how many of them I have, I still get 1. What about 2? If I plug in 2, I wind up like somewhere up here with 8, right? Because 2 times 2 times 2 is 8. And the same thing's going to happen down here. If I plug in -1 and I cube it, -1 times -1 is 1, but then when I multiply it times a -1, I get -1. And then the same thing's going to happen down here with 2 to -8. And the way these graphs look when we do them is it's got this weird curvy. I want to do that again because that was awful. It's an awful graph. Let's see if I could do better. You don't even know how hard it is. So they make something that kind of looks like this. And it's a little squiggly and it starts going up really fast. But it kind of makes that churn. And so we can put in any value we want for x. It doesn't matter. That's going to be our all real numbers, infinity to infinity. And y, same thing, right? It's going in both directions. It's going up all the way. It's got an arrow going up. It's got an arrow going down, which means, again, we have all real numbers, negative infinity to infinity. And then our x-intercept and y-intercept, same thing, right? They're just crossing at what we call the origin, where x and y are both 0. And the maximum times it can cross is 1. Notice when they both go in the same direction, whether it's up or both down, you're going to have more than one root. But if our arrows wind up in opposite directions, there's only going to be one root, right? And we can talk again, what's happening when x gets bigger? When x gets bigger, when it's approaching infinity, y is going up, so it's approaching infinity. When x is approaching negative infinity, though, going this way, y is going down, so it is approaching also negative infinity. And there's no breaks in the graph, so it is indeed continuous. This is the most boring lesson. I mean, it's necessary because you need the information, but it's a boring lesson. So this, ooh, that was the most exciting thing to happen this lesson right there. That's how boring this lesson is. So f of x equals the square root of x is what we're talking about here. Here's the thing. You can't have a negative under a square root and have a real number answer. So really, the lowest thing that we could actually input here is 0. If I put 1 in here, the square root of 1 is 1. If I put 2 in here, it gets crazy. So let's talk about what happens when we put 4 in here. All right, the square root of 4 is just 2. And you can see that we're kind of having this curve that sort of goes like this. And that is our square root function. So notice our domain of this, like we can't move into the negative because that would give us imaginary numbers, which we will be getting into if we haven't touched on them a little already. I can't remember. But that means that this one in this circumstance is going to be 0 to infinity is what our domain can be. We can also write it as x is greater than or equal to 0. And our range, for that matter, is also not going down, right? It's just going up. Our y values keep going up. And so our range in this circumstance is also going to be 0 to infinity, right? It doesn't go below that 0. Or y is greater than or equal to 0. Our only x-intercept and y-intercept are both the same. They're still at that 0, 0. And you'll notice that that is really common with these parent functions, right? Because these are the most basic function and we're kind of working everything off of the origin. When things start to move off of the origin, they're not parent functions anymore because we're like adding something or subtracting or multiplying something to that x, and that is what moves it away from the origin. So when you look at these parent functions, almost always your x and y intercept are going to be at 0, 0. So maximum number of roots we can have, clearly just 1. So as x goes to infinity, as x goes this way, right, we can see that y goes up, so it's also going towards infinity. As it approaches negative infinity, well, think about this. As far as we can get as it approaches negative infinity is to 0. So we could say that at y approaches 0, or we could just say as x is 0, y approaches 0, or as x approaches 0, because we can't go past that 0. And again, this is this one is discontinuous. And the reason it is discontinuous is it's got an ending point, right? We can't do anything with that. We can't move into the negative. It's a broken function. cube root, we kind of don't really need this much, but I kind of want to show you what it's going to look like. And that's when f of x equals the cube root of x. And what it's basically going to do is it's going to, when we did this cubic function where it went like that, it's going to do the same thing, only it's going to kind of be on the side like this. Right, and your domain would be all real numbers. I'm going to kind of speed through this a little bit now because I don't see, once you get kind of the understanding of, and our x-intercept still 0.00, right? Y-intercept still 0.00 because it's crossing at that origin. How many roots can it have? It can only cross at one spot, so it can only have one root. And I'll fill in the end behaviors on these as we go, but you can always tell what the end behaviors are just by looking at the direction of the arrows, right? The end behavior as x gets bigger, well, so as x is going towards infinity, y is also getting bigger, right? This arrow is going up, not down. As it gets towards negative infinity, right? As it moves in this direction, y is getting smaller. And this is a continuous function. Reciprocal is when your variable is in the denominator of your fraction. So it looks sort of like f of x equals 1 over x. And these kind of graph, this is a terrible drawing. Try and make it a little accurate. I am just like rough sketching these, but we should try and make it at least a tiny bit accurate. So this is when you've got something that kind of looks like this, and this is there. And then you got something that looks kind of like this. Oops, like this on the other side. And when you see this, you can go, oh, okay, this makes a little bit of sense. There's never going to be an x-intercept. It's not applicable, right? There's never going to be a y-intercept. These are like what we call asymptotes. You can't, when we're talking about a reciprocal thing, it's never actually going to get to y. No matter how big I make x in the positive or the negative, it's never going to equal 0, right? Because it's a fraction. I can't put in 0 for x because it's in the denominator, and we can never, I don't know if you remember the whole okay, no, because you can't divide by 0, right? So you're never going to see 0 as an x value because it can't be. We're not allowed to divide by 0, which means x or y will never reach 0. And so neither of these says maximum number of roots or zeros, 1, but really it's none because we're never the only way it can be, they're saying 1 because it could be like a point at 0, 0. In end behavior, you can see like as x gets bigger in this direction, y gets bigger. And as x gets smaller in this direction, y gets smaller. Well, actually, kind of the, I kind of got that backwards, right? As x gets bigger, this one starts approaching. We won't worry about that. Clearly discontinuous, right? This one also mentions asymptotes, right? Which we'll get into later. I'm not going to worry about that right now. We're going to actually talk about asymptotes as we get down, but all it means is lines that can't be crossed, right? Is there a stopping point? And for us, the asymptotes are x equals 0, right? Because we can't have an x that equals 0 and y equals 0. But we're not going to worry about that right now. This one, we're not going to do logarithmic. We'll do it just for the sake of your assignment, but it'll be super obvious when one is logarithmic. But I'll just draw the picture. We won't give all the information on that one. An exponential function, that is when f of x equals something to the power of x. In this case, we're using 2. And what's going to happen here is we're going to have something that goes like this. Oops. And that's going to be exponential. It's going to grow really fast and shrink really fast. And again, I'm just putting these in now for the purpose of you being able to see the graph if you see it on your homework. So I'm not actually filling in all the information anymore on these last two because we're not going to get into it too much in terms of graphing. But I do want you to be able to see what they look like. And a logarithm is just like taking this graph right here and kind of flipping it over diagonally. And you would get something that looks like and then yeah, I think that's about it in terms of this information. Like I said, you don't need these pieces of information right now. We're not going to be talking about this stuff, but I do want you to see these graphs. I didn't graph this one though. This one kind of goes. I thought I did graph it. Did it just disappear? Kind of like that. But these will not show up as much for you as the other ones. So in Delta Math, it's just all you do, bring up this sheet if you want to print it so you can see the graphs, or bring one up side by side with it, like just type in like graphs of parent functions and have it on one side of your screen, and on the other side of your screen have your Delta Math assignment, and you can kind of see them as you put it in, because all they're going to say is what's the parent function of this graph. They're going to show you different graphs and you have to figure out like what the parent function is. But when you see it, it's not going to be like perfect. You're going to be like, well, what is I'm going to show you really quick. Maybe it'll be quick. So this is basically what you're going to get. You're going to get a timer like this, and you're going to go, well, what kind of function is this? And you'll look at your thing, and you'll be like, oh, that is a cube root. And if you get it right, it'll move you on. What is the parent function? Boom. And it's going to kind of go like that. And you're just going to look at your graph and be like, well, which one is it? Which one is it? 1 over x. But you have the paper in front of you. I added a ton of seconds to it. You're not trying to beat it in 100 seconds. You have like 50. Once you get your score up to 15, I think it is, then you're done. That is all I have for you today.